Welcome to this explainer. Today, we're doing something really exciting. We're popping the hood on artificial intelligence to decode the core paradigms of machine learning. If you've ever found yourself wondering what is literally going on inside your favorite AI tools, you are absolutely in the right place.
So how does AI actually learn to do what it does? It's kind of the fundamental question, right? We hear the term machine learning constantly. It's in the news, we talk about it at work, it's all over commercials. But the actual mechanics of how a computer goes from a complete blank slate to a highly intelligent system, that is often totally misunderstood. It's not magic, I promise. It's a deeply logical process of learning from data. To make this a bit more concrete, I love this brilliant analogy from the NVIDIA blog. Imagine you're putting together IKEA furniture. There are basically 3 ways you can tackle it. The first way is to strictly follow the instruction manual. That's exactly like supervised learning. The second way? You just toss the manual aside, look at the giant pile of wooden dowels and planks, and start grouping them by shape and size to figure out your own patterns. That's unsupervised learning. And the third way, well, you try putting the pieces together, and if the chair instantly collapses when you sit on it, you just try again until it actually holds your weight. That brutal trial and error, that is reinforcement learning.
Okay, let's dive into this. Here is our agenda, which will act as our instruction manual for the rest of the explainer. 1. Supervised learning, by example. 2. Unsupervised learning, hidden patterns. 3. Reinforcement learning, trial and error. 4. Choosing the right approach. And 5. The summary matrix.
Let's kick things off with part 1, supervised learning by example. If you think about how we educate children, supervised learning is pretty comparable to a student learning through imitation from a teacher who holds the answer key. By definition, supervised learning means we are training an algorithm using a fully labeled dataset. And that dataset acts as a ground truth, or an answer key, to evaluate the machine's accuracy. The system is essentially learning to map an input space, say the pixels in a photograph, to a desired output space, like a text label, using direct human demonstrations. Now, what's really interesting here is how that labeled training data acts as our ground truth. We start with a labeled dataset of apples and oranges. A human has already gone in and established the rules, saying, hey, this red thing is an apple, and this round orange thing is an orange. Because the machine has this answer key to train on, when it's later fed test data, brand new, unseen images of fruit, it can extract accurate predictions. It knows what an apple looks like because we physically showed it thousands of examples. And you interact with this stuff literally every single day. Supervised learning tackles 2 main types of problems. First up is classification, identifying if an image is a cat, a koala, or a turtle. The second is regression, where the output is a continuous number. Think of an algorithm predicting a house's price based on square footage and location, or even forecasting if a student is going to pass or fail a class based on their past profile. This specific model drives massive commercial value right now simply because the problems we're solving are relatively easy for a human expert to demonstrate.
Which brings us to part 2, unsupervised learning, hidden patterns.
But what happens when you don't have an answer key? What if you just have a massive, messy pile of data and 0 human experts around to label it for you? Well, that is where our second paradigm comes in. In unsupervised learning, we hand an algorithm a huge data set of unlabeled data without any explicit instructions on what to do with it. We basically force the neural network to automatically extract useful features and find its own underlying structures. This is absolutely perfect for when researchers don't quite know what they're looking for in a massive data set. Think about having an unsorted mix of apples and watermelons. Nobody tapped the machine on the shoulder and told it what an apple or a watermelon is. Instead, it takes these mixed, unannotated inputs and groups them purely based on underlying patterns, like visual similarities in color, shape, or size, to create its own distinct clusters. The real-world applications here are incredibly powerful. Companies use clustering to group things, like separating your bird photos by feather color or beak shape. Then there's anomaly detection. For instance, if your credit card is suddenly used in California and Denmark on the exact same day, an unsupervised algorithm is what flags that outlier as potential bank fraud. It's also the engine behind association. When you add diapers to your online shopping cart and the site instantly recommends a baby bib, that's unsupervised learning understanding consumer behavior and correlating associated features to protect our data and sell us stuff. Moving right along to part 3, reinforcement learning, trial and error. You can think of this third pillar as being super comparable to how a human baby learns to walk, or how a gamer figures out how to beat a brutally tough level in a video game. In reinforcement learning, there is absolutely no labeled data, none.
Instead, we train AI agents through a strict reward and punishment system. They learn entirely by interacting with an environment, exploring brand new tactics, and getting feedback for their actions. Their one and only goal is to maximize their cumulative rewards over time.
And this brilliantly illustrates that concept. Here, a baby acts as our agent. The baby takes an action, transitioning from sitting to crawling. And as a result of that action within its environment, it reaches a bottle. Boom, that's the reward. Just like a human infant, our AI agent takes completely random actions at first, but it refines its strategy over millions of iterations strictly based on those iterative rewards. It finds the optimal path through pure experience.
This exact method is how the most cutting-edge robotics work today. Amazon uses reinforcement learning to teach warehouse robots how to navigate, pick, and move goods around. It's heavily used in autonomous vehicles, steering self-driving cars by severely penalizing the algorithm in simulations if it crashes. And of course, it's used to master video games by earning bonuses to predict the winning next step. What's incredible here is that, unlike supervised learning, this method has absolutely no upper performance limit. If the simulation is accurate, an agent can literally achieve superhuman capabilities.